Good evening, everyone. Welcome to Session 7, Day 4 of the Faculty Development Program on Deep Learning and Disease Definition. It is my privilege to introduce Professor Arup Kumar Pal, currently serving as an associate professor in the Department of Computer Science and Engineering at IIT Dhanbad. Professor Pal received his B.Tech in Computer Science and Engineering from the Government College of Engineering and Textile Technology, Behrampur in 2006 and his PhD from IIT Dhanbad in 2011. Earlier in his career, he also served as a lecturer in NIT Jamshedpur with over 14 years of teaching and research experience. Professor Paul has published more than 100 research papers in reputed journals and international conferences. He has successfully guided 12 PhD scholars with significant contributions in information security, image security, data hiding, blockchain, and DNA computing. He has received several Best Paper Awards, completed prestigious R&D projects funded by ICMR, DHT, CSIR, and C3I Hub, IIT Kanpur, and actively contribute as a committee member in the various conferences and workshops. His core research interests including information security, blockchain, multimedia security, and image analysis. We are truly honored to have him with us today, and I warmly welcome Professor Paul to deliver his expert talk. The session is yours, sir.
Good evening to all of you. Thank you, Abhishek, for your introductions. Thank you, Dr. Pravir, for inviting me for presenting my lecture in this particular options. So let me share my lecture notes. Is it visible, no? Hello?
Yes, sir.
Okay, thank you. So today I basically talk about the image analysis using the deep learning mechanism. So today basically my main concern will be the content-based medical image retrieval topics. Okay, so that will be my main concern. So this is the outline of my presentation. So here we basically talk about content-based medical image retrieval, and also we basically see what are the mechanism we basically follow in this particular process, what are the ML and DL feature, because in this particular process the feature extraction is basically one of the major concern. So that particular topics we basically learn, and also what is the advantage whenever you talk about the DL, and at the same times what are the challenges we basically face, because whenever we are learning with the whenever you are dealing with the medical data, the main concern is that the less amount of data. So there we basically talk about the transfer learning, that is another way to train the data, and there we basically talk about two mechanisms. One is the feature extraction versus fine tuning. So which one is basically gives the better way to extract the better solution. So this way we basically give the outline of our today's lectures. So what is objective? The objective of a medical image analysis is that to extract the meaningful information that basically help us for diagnosis process, even the proper treatment planning, and even in the what will be the proper treatment process will be there. So that will be the that is the proper objective behind the medical image analysis. Now, in the conventional medical image analysis, what is the practice? Now, we basically takes the medical digital data, and the expert basically examine the data manually, and basis on that, they basically give the feedback. But the expert manpower is basically limited in the real scenario. So where there is a requirement how we can make these things automatic. So that is the one of the major concern. So in this particular aspect, deep learning basically becomes a promising research area where how this deep learning based mechanism can analyze these medical images in a automatic way. So that is the major concern. So the the success of machine learning basically depends on the extraction of the suitable and meaningful data from the medical data, and here uh, the expert knowledge is also required. But in case of whenever you talk about the DL, that DL basically perform these things in an automatic way, and it basically extract the things from the raw data through the different kind of learning mechanisms, and it basically gives more informative data compared to the machine learning techniques. So that is the basic advantage whenever you talk about the ML based mechanisms. Okay, so what is the things? Now we can see that PAC is one of the standard mechanisms which is used in a worldwide, which to manage the hospital management systems, and they basically deals with a large volume of medical data, and this data is basically in a petabyte, means the size of this data is basically petabyte. Okay, means 1 petabyte is 1024 terabytes. So that is a huge volume, and the nature of this data is more complex. Yes or no? So what sometimes the data may be in the X-ray, it may be CT scan, it may be MRI, it may be PET. So there may be different kind of modalities may be there. I'll discuss what are the modalities is used in the medical imaging in the later. But in the medical imaging, so there is a lot of medical imaging is there, and this medical imaging have a lot of modalities. So we need certain mechanism. Those mechanism can handle these kind of image modalities. From there, they can extract meaningful informative analysis data so that it can give some clinical diagnostics outcome. Because the manual diagnosis may be sometimes error prone, but the automatic diagnosis can give some quick response, and sometimes where the expert is not available, and that cases this kind of practices is quite effective. So that's why you can see that the government of India also taken some initiative how to develop some AI based medical resources so that we can basically replace those kind of demand of this expertise in case of, because initial level we can give the initial solution based on the AI based technology. Okay, so this is the basically deals with the patient specific, and it basically deals with a more drastic way compared to the conventional way. That means it basically beyonds on the more generic, and it basically gives some more details of the what kind of possibility is there, what kind of possibility, what are the possible treatment may be possible. This kind of more details means it can give more details where it can provide the solution. So whenever we consider the diagnostic approach traditionally relied on physicians' accumulated experience, recalling similar cases from memory to inform a new diagnosis. But in large searchable images, archive could make this process easier to the expertise so that they can get the more relevant case studies, and basis on this case study, they can take the necessary steps for the treatment process. So here the image retrieval may be one of the great solution. So now in this particular retrieval process, I want to show you that traditional retrieval process, there is a two types of mechanism is there. One mechanism is basically called as a uh, text-based retrieval process. So what is the text-based retrieval process? Now, say for example, you have a given one patient records. A patient record is basically stored with the patient name and patient ID like this. So whenever you are giving this patient ID and patient name, you are basically retrieving that particular patient ID and patient CT scan or X-ray data, and you can visualize these things and you are getting these things. But as a expertise, suppose I know that that some patient having this kind of condition and they have given this kind of treatment. But with the help of this text information, that means if I say that which patient, it is quite difficult to remember all those things. So that means the text-based retrieval process is not quite suitable in the real-time scenario, basically in medical science, because medical science, it is not quite feasible to remember which patient's case study corresponding, you have to remember it. So that means uh, here there is another mechanism is also there, that is called the image based searching process, and another text based retrieval searching process. And generally basically talk about like a file name, keyword, location, this kind of information we basically provide to retrieve the content. Okay. So there is another limitation of a text-based retrieval searching process. Suppose you want to express this particular image. So somebody says that it is a horse, somebody says that it is the image of forest, somebody says that it is the image of grass, tree. So so many people can give the tag according to this. The same things happened with the medical imaging. So medical imaging, a particular image can be represented by the different nomenclature. Yes or no? So that means that way, if you want to search, then it is quite difficult to get the meaningful things. That means the TBR process is basically have 7 limitation. The major limitation is that so if you have a large data size, so then the tagging is basically tedious process. The database annotation is basically one of the tedious process. That means each and every database you have to manually, you have to tag it. So sometimes this tagging is not a correct. That is called the wrong human perception may be occurred in this particular process. Sometimes you can give the wrong keyword. The correct keyword is not associated. So that means it basically the whole process may be continuously, it may be the goes wrong, and at the same time this whole process may be the tedious. So that is one of the challenge in this particular process. So here we can see that the content based image retrieval, that is one of the popular terminology. So what is the content based image retrieval? Now we basically search the content with the based of the actual content rather than the giving the content of the giving the actual tagging value. So say for example, suppose I'm giving the query image, and based on this query image, we basically extract some feature. Already I basically perform the similarity matching with respect to this feature, and basis on that, those having the similar features, those similar images can be retrieved in this particular process. So similar way, if the medical imaging, if you have some similar medical query image in terms of medical image, I basically retrieve the similar medical images, and from there I can retrieve the case study of the corresponding patient. So that way we can deal with the medical imaging. So that means content-based medical image retrieval. So that is the way I can deal with. So what is the general framework? So in terms of a content-based image retrieval, so there is one will be the content on it. That means a hospital basically generate the medical images, and from these medical images, we basically generate features, and that features will be stored in an image repository. That means every image corresponding, we basically generate a feature vector, and that feature vector dimension is quite less compared to the original image, because the straightforward comparison is not a more suitable. So rather than comparing the straightforward, we basically find out the most salient component, more salient component of the image, that is called the feature vector. And now the similar way, we basically takes the image, and from there we basically extract the image, that is the feature extract, and we perform the similarity measures, and after that we basically based on the distance measure, we basically give the retrieved images. So this particular process can be realized. This diagram basically shows that how the content-based image retrieval system works. Okay, so it basically works in two phases. That is offline mode, and another is the online mode. So in the offline phase, the retrieved database is processed by extracting the visual feature, that is color, texture, shape, or sometimes deep learning based descriptor from each image. And these features are organized into an efficient database index to enable fast searching. In the online page, a user provides a query image, and the system extract is featured in the same manner as the database images. Then what happened? The query feature are then compared with the index database feature using the similar measures. The similarity measures, we can use the suitable distance measure like Euclidean distance measure like marathon distance, all those things. Then images are scored or ranked based on their closeness to the query. A ranking step may be applied to the initial result through the relevance feedback or semantic analysis, ensuring better accuracy. Finally, the system returns a list of retrieved results, displaying the results. Those are most similar to the query image. So that is basically occurred in a two phase. So that means offline phase, this is the most huge computation overhead, but this online phase has not that much. That is it can move in a quite faster manner. So that means this step is tedious, but this step is not that much tedious. Okay, so retrieval process is very fast because already the feature vector is stored in the feature database. So based on this major steps of this severe process can be categorized in the 4 steps. First step is the feature extraction. That means we have to extract the salient component. That salient component may be in terms of a handcrafted features or maybe the deep features. Okay, and actually in this particular session, we basically show you how the deep features can be used to extract these particular things. But both the way you can extract the feature. And after these things, we basically extract feature vectors will be stored in the database, and that will be considered as a feature database, and that will be used to similarity measurement process in the later stage. And in the similarity measurements, we basically use the same query feature vector, which is taken from the query image in an online mode. So that these two basically done in the offline phase, and this is basically done in the online phase. And here the similarity measure is basically carried out. And after that, all the distance measures, based on the distance measures, the relevant images has been displayed, which are more close to the query image. Say for example, suppose we have a query image, this one, and according to the feature vector, we basically perform the similarity matchings, and according to the similarity matching, we basically retrieve all the X-ray images. Those are close to these particular images. Okay, now in generally, there is a handcrafted features is basically used for this particular process. There is a three types of handcrafted features are basically used. One is called the color features, another is the texture features, and another is the shape feature. And sometimes we basically consider the combination of these three in a proper way to design more suitable CBR process. Now, in severe process, one of the big challenge is the semantic gap problem. So, what is the semantic gap problems? Now, semantic gap problem means uh, actually what is machine is perception and what is human being is perception. Because sometimes these two image as a human being, we can say that both images belongs to the same category. But machine perception, they basically sees that both may not be the same category because here the background content is more compared to the foreground. Yes or no? So human perception, both the image content are same, but the machine perception both are not the same. So that is the one of the big challenge. Like there is another problem here. Like this is the one of the component. This particular image for the machine perception, we can see that it may be the apple. Somebody says no, it may be the guava. According to the machine perception, we can retrieve a different kind of structure. Means if you follow the structure, then you can get a different kind of structure outcome. If you follow the color, if you follow the structure, you'll get that. If you restrict the color, then you'll get that restricted outcome. So that means the machine cannot be understand whatever the human being can be understand. So that is the one of the semantic gap problem is there. So here uh, here deep learning basically deep learning, which is basically particularly convolutional neural network, is basically play an important role. Instead of considering the handcrafted features, deep learning models, which is capable automatically learning a hierarchy of increasing complex and abstract feature directly from the raw pixels. And this ability representation from data that is more important to develop more robust systems. And these particular systems basically achieve the feature in a different level, like a low level features. Sometimes it may be the mid level features, it may be the high level features. Now, under the low level features, we basically see the basic structure, like a it may be the age, it may be the color, it may be the gradient, like this. Whenever we talk about the mid-level features, we basically see the combination of age and texture, or sometimes we basically see more complex representation of the low-level features. So that basically more suitable whenever we talk about the pathological or medical content analysis process. So mid-level feature basically play an important role. And another is the highest level. So this basically at this stage, yeah, we basically takes more relevant structure, like a what is the tumor structure, what may be the means what may be the category of the structure, means a more detailed structure of these particular things may be acquired in this particular high level structure. So the deep learning basically gives the more informative content in different hierarchical levels. So that is the more advantageous compared to the handcrafted vision. So if we compare with respect to machine learning, if we consider with respect to machine learning to deep learning, so we have basically compared with respect like text-based retrieval. Another is the traditional content-based image retrieval, and is the deep learning-based Okay. So, whenever talk about the deep learning, so it basically having the basically three level of features, like a low level features and mid level features and high level features. And these particular features basically helps us to develop a most robust diagnostic systems. Okay, that basically more suitable to analyze like a medical imaging, like X-ray images or CT scan images or X or all those images. Okay, so so here if you see these particular things, that the traditional machine learning to deep learning is basically improvement of changing the solving a complex perception problem, like means whatever we see in the conventional like a machine learning base, so that means handcrafted features basically see or knowledge of the expert is required, but in the deep learning it basically learn from the pixel automatically, so that it can design a robust system in this particular process. So that is the one of the advantage. So if we compare these particular things, so that is it is manual, traditional content-based images, semi-automated. That means we basically train the handcrafted feature, but it is basically fully automated. Yes or no? So definitely, sometimes the deep learning basically work as a black box, and but the thing is that the performance of deep learning has been seen more better than compared to the other approaches whenever you have a efficiently more number of data set is available, because data set is one of the very important whenever you are dealing with the deep learning based techniques. Okay, but in the medical imaging, this is the one of the major concerns. So that particular things I want to address in this particular lecture. So what kind of medical imaging modalities is there? Like X-ray, CT, MRI, or PET, or microscope. Those are basically used imaging techniques. Like X-ray are basically quick and yeah, mainly used for the bone or fracture or chest imaging. But whereas the CT scan basically combine multiple X-rays to produce cross sections images, provide detailed 3D views, bone tumors, or even some internal injuries through higher radiation may be possible in this particular process. Whereas the MRI basically uses the magnetic fields or radio waves to generate more detailing of these particular things to enter the contrast. So that is the another way of representation. Spate scan also another way of representation that basically sometimes is basically useful for the cancer treatment or brain or heart studies. Ultrasound also give the real-time radiation-free imagery commonly used in studies for the organ segmentation, motion tracking, or disease classification. Okay, like it may be the abdominal or cardiac vascular microscopy. It basically studies in case of microscopies, bioscopy samples, all these things. So this is the different kind of modalities is there, and according to different modalities, there is so many medical imaging techniques is basically vast in this particular area. So this is another area like a dermatology. It is basically deals with the skin images. Fundus ophthalmology, so that means it is retinal images. It basically deals with retinal images. Endoscopy, dental imagings, nuclear medicine. So that is a lots of modalities is there, and there is a lot of research is going on in this particular area, so that we can develop a robust particular things. Now, whenever we talk about the deep learning with medical imagings, deep learning having uh, is very powerful at recognizing object, and also at the same time it is also more suitable for classification different categories. So in medical imaging, this detection as well as categorize of the abnormalities of the diseases is very, very important, and that can be effectively done using the deep learning algorithms. So now in this particular process, so there is this, what is the advantage? Now advantage is like that, it basically supports automated feature extraction process. It means that automatically the system can learn, extract complex structure from the raw pixels to identify the patterns of the digits. That is the one of the major concern. Another thing is that it basically improve the diagnostic accuracy, because deep learning techniques basically deals with a large amount of data. So naturally, its accuracy is quite high compared to the traditional mechanisms. And also it enhances the image quality and reconstruction. So that means that deep learning based mechanisms can be used to enhance the image quality, means it can be used as a image enhancement techniques process also. That is another area that is also useful. That means because in the medical imaging, whole image content is not necessary for your study purpose. Uh, some subjective area is required for in your study purpose. So segmentation or localization is very, very important. So that means automated segmentation localization is basically is very, very important in this particular process. And there basically medical imaging can be segmented, or localization can be done using with the help of DL-based mechanism. So, so here, this kind of application, this kind of operations can be achieved with the help of the large volume of medical data, uh, uh, with the large volume of medical maker, and that makes the process more quite easy, and more, and performance is quite high compared to the conventional practices. But the challenges are like this. The scarcity of annotated data, that is one of the challenges, because deep learning architecture basically requires use large label data, but sometimes due to the restrictions of the collection of the data, or sometimes there is so many restriction is there in for the collection of data. But if somebody have the data of the medical data, they are not able to share the data in the globally, because that is having some kind of restriction. That means we basically see that the data sharing is another challenge in this particular process. So scarcity is another issue in these particular cases. So how the scarcity of this data can be handled, and there we basically overcome this kind of problem through the annotation process. Another is the annotation cost, because sometimes whenever it takes the data, due to the expert knowledge is also required to annotate this particular data. So cost is also required in this particular process, quite high in this particular process. We also received one project from the ICMR, there the major funding is then given for the data creation and data annotation, rather than the development of this technology. So five AIMS institute is there, along with the two national importance like NITs, one IITs is there. But major funding is given for the data creation and annotation process. So that is, annotation cost is very, very high in this particular process. And another challenge is that data quality. That means medical image, whenever you acquire, and that can be acquired in a different diverse imaging systems. And there may be the possible that image may not be consistent, and sometimes due to the presence of different kind of noise, image may be degraded. So we have to overcome this kind of scenario. So that means image restoration process is also required in this particular process. Another is the data bias, because imbalanced data set is one of the bottleneck in the deep learning model. So that means whenever you want to train the things, data bias is also one of the challenge. That means imbalanced data set is not required in this particular process. Data privacy, that means sensitive nature of patient data should not be presence in the outside of the system. That means how the data should not be shared with the concern of the patient. So that is one of the big deal in this particular process. So this is the big challenge. So to solve this challenge, we basically see that we basically follow a different kind of patches mechanism. That means a large image is divided into small patches, and that patches is considered the another images. And sometimes we basically use the data augmentation process. That means and the actual image is artificially transformed into another image, like a different kind of rotation, scaling, and flipping operation to generate a huge volume of data. That is called the data augmentation process. And that is a very important transfer learning, because transfer learning means already we are using the pre-trained networks that is already trained with the natural image data sets, and this data set will be used to train our medical data for getting the desired outcome. So how the transfer learning is more effective in this particular process, that particular things we basically see. Now, in medical imaging, two common strategy, that is deep learning, that is feature extraction and fine tuning, are basically used in this particular process. So the first strategy, that is feature extraction, it basically takes a pre-trained networks which is basically trained on a large data set, natural image data set like a ImageNet, to generate a trained networks that is basically effectively work on natural data set. And now we basically use this particular network to use the medical images without training the entire deep learning networks. So that is one of the objectives. So these extracted features, whenever you use these medical images, already the pre-trained networks, these extracted features can be integrated into existing image analysis pipeline, so which basically saves time as well as computational resources in the network layer. And another is the fine tuning. So fine tuning is what? Now it basically adopt a pre-trained networks, but here we basically adjust some learning features, like sometimes we basically tune these particular parameters based on this medical data to get the more desired outcome. So what is the way you can tune this data, tune the data that I basically want that will extract? So there is a two mechanism. One is the fine tuning mechanism. That means the existing networks will be tuned with respect to the medical data. That is the another way. So so what is the way? And we basically see that there is a two mechanism is basically used. Like suppose you are using the VGG16 networks. So in this particular cases, what happened? Now we basically use the freezing concept. So what is the freezing concept? Now some layer we basically freeze in this particular process, and some layer we basically unfreeze in this particular process. That means during the training process, the freeze layer will not update their weight value. Okay, and some layer will be updated, their weight value will be updated in this particular process. Okay, so this freezing concept will be used to train the networks. So this kind of approach basically helps to train the medical data in a more efficient way, and in a because large already, because the small volume of data from the scratch, if you want to train, it will not give the good accuracy. So it is better to use the pre-trained networks, but don't disturb the networks. So you freeze some basic layers, and but some layers you can train with respect to your using your medical data. So that is the thing. So that I basically want to give one demonstration how the freezing and unfreezing concept basically improve the performance of this medical image analysis process. So that basically wants to show you. So here this particular process, a fine-tuning process, this freezing and unfreezing process, whenever you have a particular content, that means that is you have a this main core idea is like that. When the fine tuning, that top layer already it is top layer, it is basically huge computation over is required in this particular process. So this particular layer will not be touched. We basically touch those layer having on that much computation over it, and that particular layer we basically tune with respect to your data set, so that the overall computation not be increased, and the performance should not be degraded in this particular process. Okay, so what is the basic steps in this particular process? Now we basically take the input, we basically take the pre-trained networks, some bottom layer will be the frozen, and that basically extracts some basic structure that is the common, and top layer will be the unfrozen, that basically used for specific tasks. So and this top layer will be trained with respect to your medical data, and these output features will be given to the new classifier for the train the data, and that will give the final outcome. So this particular process, so we can see that the fine tuning strategy pre-trained network will be initiated. So first it will initiate a pre-trained convolution base like a BGC16 weight value will be loaded, and then we add a custom classifier on the top perform to specific tasks, so that what kind of operations we can see, whether it is a disease classification or not. So initially we freeze the convolution base to prevent the weight from the being updated, and train only the new classifier for the few epochs. So these steps allows the classified lump stable initial weight without disturbing the general purpose feature in the base. Once the classifier is reasonably trained, we unfreeze a few of the top layer of the base model, those flows of the output which capture the more task specific pattern. Finally, we retain the model which is unfrozen base layer and with very learning rate. So finally, we basically get some more accurate and more desirable results with respect to this particular process. So here we have given one demonstration. So my scholar, he will given one demonstration based on with respect to the VGG16. That is how the VGG16s can be used to capture the medical image in a transform learning approach. Because the one of the major bottleneck of the medical imaging is that less amount of data. So how the less amount of data can be trained with the help of the transform learning, because the model can be changed, because our objective is how this approach can be used so that the medical imaging, because the medical image is the major bottleneck is that we have the less amount of data. So how the less amount of data can be used to give design a robust network. Okay, so so these particular things will be presented by my scholar. So let me finish my presentation, so then he'll present these particular things. So in this particular process, we basically see that that using the transfer learning process, we have basically want to see one cancer data set. We basically use the one of the data set, skin data set we have taken, and that particular data sets having very less amount of data in some category. Okay, so to overcome these particular problems, we basically use different kind of augmentation approach to increase these data sets, like a flipping, flip horizontal, flip vertical like this. And after that, we can see that this particular data set has been accuracy has been increased in a certain category, but certain categories accuracy has not increased that much, because the number of data sets is not that much presence in that particular process. Now, this is the some representative outcome where if you give this kind of input query image, and this is the corresponding outcome with respect to this query image. And this particular, this is the another outcome with respect to modified BGG16. And in this particular modification, we basically use a different optimizer to improve the performance of the conventional BGG16s. And here we have seen that that in every category, the accuracy has been drastically increased compared to the previous one. So that means whatever the accuracy was there, like in this particular cases, we have used the different optimizers so that learning rate can be decreased and we can achieve the more accuracy in this particular process. That is the more objective. So that means what is the our main concern? The main concern is that you have to use one more robust architectures. That architecture can be used in a transfer learning process so that you can achieve the desired outcome in this particular process. So what we have seen in this particular process, we have very small data. We have seen that whenever we are using a very small data set, there is a possibility that the training is very quite fast. We have only updated very few weight in this particular process. Computation, it is very cheap and it is effective even for the small data set. But the disadvantage is that it is very less flexible because it is not able to learn the feature when you have a more complex or more various medical imaging modalities in this particular process. So that is another demerit in this particular process. Another advantage is that it basically, compared to the fine tuning, it has basically having higher performance, like can achieve higher accuracy than feature extraction process, and it is basically more powerful compared to the more flexible than training knowledge, but computationally expensive, require more data, and basically if your data is too small, then it is not work in a that much effective way. So that means overfitting problem may be occurred in this particular process also. So if we compare these things, so that means feature extraction process is quite fast, but fine tuning is basically slower. It because basically required data is basically more data is required in fine tuning process. Computation is quite high compared to the feature extraction process. Performance definitely is better in fine tuning process, but there is a risk of overfitting, and the main action is unfreezing, which layer is you have to unfreeze. That is the one of the major concern in this particular process. So here, let's see the choice between the feature extraction and fine tuning transfer depends mainly on two factors. That is size of the available data set and its similarity to the data set used for pre-training. So when dealing with a small data set that is similar to the source data set, feature extraction basically prefers strategy. So in this case, the pre-trained networks feature are already well suited to the stacks, and retrain the model through the fine-tuning make lead overfitting because the limited data. So if we have a large data set, then similar data fine-tuning becomes the best options. In the other case, when you have enough available data sets, in that case, the model can adopt its learned representation to the target domain more effectively, which often results in higher accuracy and stronger performance. It basically provides the stronger performance. For a small data set that is very different from the pre-trained data set, the situation is more challenging. So the pre-trained feature may not fully capture the new domain's characteristic, simple feature extraction from earlier layer. So the most reliable solution in this scenario is to acquire more label data to improve the learning, and which is one of the big challenge, because in the data set collection is very, very big challenge in this particular process. So when the working in the large data set, that is different from the source data set, fine tuning may many layers or even training a model from the scratch become feasible. So data proper data collection, that means the large data. So that means the data set size and signal guide the optimal strategy choice is very, very important. According that depends on your data set and what kind of problem statement you are working in this particular process. So that is one of the major concern. So deep learning is basically one of the very important tools, and definitely its performance basically solely depends on your data sets. And if you have a large volume of data, so definitely your performance is very improved drastically. So and at the same times, but the big challenge is that the data, because if somebody have the data, because the data sharing is not is that much easier, because there is so many restriction is there in this particular process. So we have to think about different kind of alternate mechanism, so that with the help of the limited data, how can improve the performance using the like a fusing some local global features, or using some more advanced architectures like a Bayesian transform or hybrid models to improve the performance. Even the federated learning or ensured learning may be the one of the solution, where with the help of the federated learning and blockchain based mechanism can resolve the data sharing problem also, because in that case you no need to the big challenge of the data sharing can be overcome if you consider the federated learning along with the blockchain. So that means these strategies also overcome this particular limitation. So this definitely the performance of the machine deep learning solely depends on the huge volume of trusted data, and this can be achieved whenever you have a huge volume of data, and other than you have to think about some alternate mechanism. So now I'll request my scholar Sukla to present how the transfer learning can be more effective solution to achieve the desired solution whenever you have a less amount of data sets. Okay, so Sukla,
Okay.
please.
Okay, thank you, sir. Now, let me just present. So in this particular notebook, through this collab notebook, we'll just see how a particular backbone network, let's say your VGG 16, in this example we have taken, how we can extract the pretend features and we can utilize further for your medical research. Now, why this important to use any transfer learning backbone networks, sir has already discussed. I will just show how these features are here shown. That means how the transfer learning or the pretend features, if we extract the pretend features, then how it can be visualized, how the features are learned, or the weight matrices are getting activated onto the raw pixels. That we will just show and compare with compare with the simple CNN architecture, how it is distinguished with the pretend features as well as the traditional convolutional features. Okay.
Data to a central server for analysis.
Okay, so let me connect my notebook. So here I've just taken one particular sample image, and we will just see how this pretend features is getting, activated weights are getting visualized in that particular input image with the pretend features, as well as what are the features being learned with a simple CNN architecture without training this CNN architecture, as well as without fine-tuning the backbone networks, right? You can use any backbone networks in your case, if you, in your medical data, whether you can use VGGNet, whether you use ResNet 50 or efficient net or any vision transformer models, that's no issue. But in case you have, in case of this particular, in case of this particular demonstration, we just show this how this base model, that means we have just downloaded the pretent weights, that is the VGG 16, right? And we have got this particular input image, right? These skin lesions to detect if any cancer cells is present or not. That is already present in the data set, right? That is already cited in the particular slides that was already shown. So we'll just visualize through these particular plot functions how the feature maps are getting activated through the pretent networks, right? So we just, if you go through the particular architecture of this particular VGG net architecture, you see there are two convolution layers. That means in this particular block, let's say there are 5 blocks, right? Block 1, block 2, block 3, 4, and 5. And the first 2 blocks has 2 convolution layers, right? And in between there, we have the max pooling to, reduce the spatial dimensionality. And again, we have these 3 convolutional layers 3 times. That means block 3, block 4, and block 5 has the 3 convolution layers each. And why these convolution layers, number is not, is not set. It is optimized in their paper. This particular works best performance in the ImageNet data set, right? And finally, we'll have the fully connected layer, which is known as the classification part. So what are the feature extraction part? After this block 5, right? Block 1 to block 5 is your classification or feature extraction part. Right? The features are getting fine-tuned here in each of these blocks. And next, we have this fully connected layer for your classification part. Here, 1 cross 1 cross 1000. 1000 means your 1000 ImageNet classes are there. And if you have the 2 classes, then you will have 2 class here, 3 class problems, any of the class problems according to your disease classification or the segmentations, it will accordingly, it will be adjusted, right? In your model, the top layers, that means your fully connected layers, right? So from this particular block 1, that means the initial layers, block 1, block 2, how the feature getting, feature maps getting activated through the weight matrices, the pretent weights. Pretent networks means you have the pretent weights that is trained on the ImageNet data sets, right? And how these weights can be utilized for this transfer learning concept for a new data set. For example, your medical data sets that are smaller in size, these pretent weights will be very much useful because you don't need to learn anything about the natural images or images in particular, right? So this is the similar block architecture in different way. So the convolution layers are the first 5 blocks, right? 5 blocks. And initial layers are the block 1, block 2, and the mid layers you may consider block 3, block 4, and the more abstract representation of the pairs are given in the block 5 in the VGGNet architecture. In any of the architecture, whether it is EfficientNet or any other DenseNet or ResNet or vision transformer, you'll have different issues, but the similar feature extraction layers will be there, right? They have optimized their computational, in terms of computational efficiency, in terms of their multiplications of the operations. They have reduced in their paper. That is a different issue. And then finally, we have the fully connected layer for the classification. And the output layer, if you have any number of classes, that is the, it will show, right? So with this VGGNet, you can replace it with any other architecture, no issue. But how the pretent architecture works. So if we run this particular block, see, we are seeing only the block 1, block 3, and block 5. After these 3 blocks, what are the feature maps that getting highlighted? See, according to this particular architecture, block 1 has the 64 filters, and block 3 will have the 256 filter. Here in this architecture, you can show the dimension already, the output dimension already given, the 64, 128, then in block 3, 256 dimension will be there, and block 4, 512, and block 5 will have 512 again, right? These are the filter maps. What are these filter maps? It's basically a weight matrices. This weight matrix and bias are called the parameters, number of parameters, right? So here, in this case, if we run this particular block, if you want to visualize this block 1 and block 2, block 3 and block 5, the intermediate blocks, initial to the final blocks of the VGGNet architecture, you see that for this input image, if we activate the grad cam or if we, the particular pixels getting through this weight matrix, the 64 filters, whether it is for in case of block 1, then we'll see this 64 feature maps, right? For this particular, in each of these filters, we'll have different visualization, different feature learning, right? And because it is a pre-trained network, that means here in this case, the base model we have set is trainable. The base model dot trainable. That means VGG60 model dot trainable is set to false. That means we have freeze this particular convolutional base. That means the whatever the weight matrices is learned, that is now fixed. That is the static right now, right? It will not learn anything. Whatever the learn through the ImageNet, that particular weight matrices are getting fixed here. And through these weight matrices, we are just activating what are the low-level features, whether it is textures, any color gradient, or any other getting activated. Blue, darker blue means nothing is getting learned, and more of the highlighted in the yellowish, that means the weight matrices are more in this particular pixels, right? So here 64 feature maps there, and we can see that the some of the feature filters and able to learn correctly visualize or whatever at the low levels they are trying to activate these feature maps, right? Now if you try to visualize the block 3 here. Here are the block 3. That means we have gone too far. That means initial levels we have is a block 1, and we have seen the low-level features, textures, color gradients, or any types of low-level features are getting highlighted here. And the more we go towards more deeper layers, that means here in the block 3, we can see the more abstract representation of the feature maps, right? More abstract representation of the feature map. Though these are the static, the whatever learned from the ImageNet features, right? We have frozen the pretend weights. So here, that's again the 256. I think for this block 3 output of this VGGNet blocks, right? So here 256 more abstract representation is shown in this particular. Because the train already trained on the ImageNet, right? And again, if we plot this block 5, that means the final block of the VGGNet, that the representation here is more abstract. That is not possible, cannot be achieved with the traditional handcrafted machine learning features. This more abstract representation only machine can interpret, right? And these are the abstract representation of the final layer, right? And how these are the 512, I think these are the 512 filter maps, right? We can see the more abstract representation of all of these filter maps, right? Now, if we want to fine tune this particular frozen initial layers, fine tune means you are just freezing out the initial layers, and at the final convolution blocks or the block, you are just training the final top layers of your model, right? Top layers of your model. And now several research are already done that we need these low-level features, the intermediate level features, as well as the more abstract level features, right? So we can combine these intermediate features also to make our final feature output. That is also done in several research or medical imaging process, right? So in the fine-tuning, what we just save the pretend weights and reload it. And here we just set the initial layers are the frozen, that means the trainable is false, and we set the trainable only the final layer, the final block in case of trainable is true. That's it, right? And here this will be the particular VGG16 architecture in the block 5, the 3 convolution, right? There will be here non-trainables, total trainable parameters is 0. Why? Because we have already frozen these trainable parameters. So those are all non-trainable. That means static weighted features, right? And here the similar things will happen. We can see the feature maps in every run. If I run this particular cell every time, the block 1, block 3 will give the same feature maps, right? But the block file will, it will again and again, it will give different outcomes with this block file, the more abstract representation. In that particular layer, we will train here in this block 5 layer, we will train again and again with our new data set, with our medical, any modalities of the medical image we have present, right? So in case of smaller kind of data sets, we have this advantages of the transfer learning. In any of the other data sets also, if you have more number of data sets also, in that case also, these pretend features are very much effective to get the more improved accuracies or precisions, right? So if you want to if you just give the simple CNN architecture, just like just one convolution, there are 3 convolution layers. In between, there are max pooling layer, right? And if we just visualize these 3 convolution, right, with the same image, see, these are the initial level, the first convolution, the second convolution, and third convolution. But these are not as good as the learning for the pretend weights, right? These are still, after this last layer of the convolution, still these are not abstract, right? The abstract, we need more number of convolution in that case, right? But we achieved through this VGGNet pretend weights already with the block 5. That is the main advantage here. So the final conclusion will be that VGG16 maps, we with the pretend weights, we extract the low level features as well as the abstract level features. And in this simple CNN maps, if you untrained version of this simple CNN, we will have random filters, noisy blobs, we'll see in this case, right? So through training, more number of training epochs will be required in case of this, if we start from this scratch. And in the pretend networks, we can have more improved features, improved performance in case of this. Now, further research for if you want to do any further research, you can replace with this base networks with the recent any state of the art, let's say efficient net, any base version of the efficient net, and you can extract each of these blocks, right? And you can process with the segmentation task in the fully connected. You just paste, you can implement the pixel-wise loss functions here with the ground truths or the annotated levels, right? Small amount of data, you have the annotated levels. There is not available large amount of annotated data available due to the manpower and all those expertise requires, right? So in that case, the segmentation and localization tasks also be performed. And accordingly, you have to fine tune the features, right? That means in intermediate features, you can fuse intermediate features, you can fuse with other local and global perspective. You can do it, you can train differently, you can train, let's say, in a local manner or in a federated learning way, right? With the small data sets, and you combine them in a central repository, right? So there are a lot of scope in this particular domain, and according to your data, whatever you want to perform, whether it is segmentation or classification, based on your data, your architecture should be accordingly developed. The same architecture will not give the best performance. You have to enhance the feature extraction process or the fusion mechanisms so that you get the improved performance. So that's all for this demonstration. I hope things are clear.
Okay, sir, any questions?
Yes, sir, I have a question. Sir, I have 3 class of images. Each class I am having 100 set of images, sir. 100 images I am having. Is it possible to do image classification with 300 images in total? Each class 100 images.
Okay, so actually you can perform the classification task, no issue, but you have to use the transfer learning as your data set is very much lower. We need more data to learn a particular deep learning model from scratch. So you can use the transfer learning, you can use the pre-trained networks, any of the pre-trained networks, right? And you can check for yourself which pre-trained network is working fine with your new data, and accordingly your fully collected layer will be set to your 3 class, right? And then retrain your model. But before retraining, you can also check if your classification, that means your data, can be augmented further with the, just as sir has shown in the slide, if you can augment the data further with the all the augmentation mechanisms, right? You can do it in a 300 to 3000 by doing all the augmentation, right? You can also perform the augmentation, and you can definitely your work will be done, no issue, right?
Okay, sir. Sir, in augmentation,
Actually, generally 10,000 images required for any kind of application. So if
okay,
it is
okay,
hundreds,
sir.
it is quite difficult.
Okay, sir.
Okay, so
Actually, sir, these are scanning electron microscopic images. These images are I just got by paying only, sir. So that's why I'm having a limited number of
I got it. So
images.
then you can take in patches and you can do it. What is the dimension of these images?
It is having 512 cross 512, sir.
Okay. Then you take the augmentation. Augmentation will be the another way.
Sir, particularly in augmentation, how to increase the number of images, sir? We can set parameters in coding, or else how to
There is a
increase
coding
the...
is there. Augmentation coding is there. Shukla, can you?
Okay,
So
okay,
you
sir.
can perform any of the augmentation techniques. There are a lot of repositories available. There are flipping, horizontal. The same image is transformed into this many types of,
Yes. Okay,
right?
okay, sir.
No
Yes,
issue.
sir.
Okay.
Okay, okay, sir. Thank you. Sir, could you suggest me particular task of limited data sets which I am having? Any CNN image classification model? Would you suggest anyone, sir, for a low
Sir,
number of data sets?
Sir, actually, it depends on the, you have to experiment on the backbone network. So what are the pretend networks available? That means DenseNet, RaceNet, or EfficientNet. You have to try it with your images, right? Feed it to the model and try to retrain the model and see the performance. Then you will able to decide that which backbone networks to further refinement is required. Okay.
Okay, thank you, thank you, thank you.
Already this Colab code is given in the Colab, so you can download it. You can check it. Already I shared this my PPT with your provisor. The provisor will share your PPT, then you can get the Colab link.
Okay, sir. Thank you.
Okay. Okay.
Any other queries?
Okay, Dr. Pabi.
Thank you very much, Professor Arup Kumar Paul, for an enlightening session on anomaly segmentation in brain MR images. Has given us valuable insights into the practical application of deep learning in medical imaging. The clarity of concept, along with your rich research experience, has truly inspired us and added great value to this FDP. We are grateful for the time, effort, and valuable contribution to this program. Thank you, sir.
Thank you. Thank you. Thank you. Thank you, Dr. Pavi, for inviting me for these occasions. Okay. So I am leaving the session. Okay. Thank you.